In this video, I want to introduce the basic model of quantum computation called the oracle model. And so I want to talk about this quantum oracle. And essentially, a quantum oracle is some unitary function, we'll call it u of f, which executes some function f of x for us. And I'll get into the details of how it actually computes f of x, because remember, we require that this transformation be unitary, and most interesting functions are not unitary. So we need a way to encode this in a bigger transformation that ensures that it'll be reversible. And the reason we call it an oracle is because in this sort of analysis of a quantum algorithm, you don't bother yourself with the actual details of how u of f is implemented. You just take it as a kind of black box function, and then you see what kind of information can I extract just with access to this unitary. And this leads to a very interesting kind of analysis that you can do for quantum algorithms and show very rigorously that you obtain speedups over a classical computer. Now, in general, how is this unitary f going to compute f of x for us? A naive approach would be to imagine some oracle that just takes your input x into some f of x. But I'll show now that this is not always reversible. It's not always unitary. Actually, in most cases, it's not, because f of x is likely to be something that's not reversible at all. Here's a simple example. Imagine f of x is just computing the XOR logical operation on a binary bit string x with 2 bits. So this has 4 possible values for 2 bits. We could have 0, 0, 0, 1, 1, 0, 1, 1. And the values that we're going to get for XOR here is going to be 0, 1, 1, and 0. So if we compute with this naive approach just f of x, we might obtain 1 over here, but we don't know what we came from. It's ambiguous because it could have been 0, 1 or 1, 0. And this is what I mean by it's not reversible. And of course, this is just a simple logical operation, and already we have things that aren't reversible. So you can imagine more complicated f of x or more complicated functions are also going to be non-reversible. So we need a smarter way to actually compute this function f of x for us within a larger unitary. And in order to introduce how we're going to do that, I first have to talk about multi-qubit systems, because we've only been talking about 1 qubit until now. How can we introduce 2 qubits into this whole picture? So let's say we have Q1, it's qubit 1. I can just say we have another one over here, Q2. But this ket notation, putting them side by side like this, implicitly means you are taking the tensor product of the two. The tensor product. So what is a tensor product? And I think the best way to think about this is to put these back into vector form and observe what it does. So Q1 is just a 2-level vector. We'll call it alpha 1 and beta 1. And Q2 is the same thing, just with different probability amplitudes, or they could be the same, but in general they're different. Now, Q1 tensor Q2, and these have kets. Q1 tensor Q2 is alpha 1 times alpha 2, alpha 1, beta 2, alpha 2, beta 1, beta 1, beta 2. So you sort of multiply across all the different elements and you obtain a larger superposition of the 2 component superpositions. And this just looks like ordinary multiplication if you write out your qubit in a different basis. So let's say we have Q1. We can write this given the way I described it up here, in the computational basis, this looks like alpha 1, 0, plus beta 1, 1, and then Q2 is alpha 2, 0, plus beta 2, 1. So this tensor product is really just ordinary multiplication when you look at it like this, in terms of what it's going to do to this kind of format. We'll have alpha 1, alpha 2, 0, 0, plus alpha 1, beta 2, 0, 1, plus beta 1, alpha 2, 1, 0, plus beta 1, beta 2, 1, 1. And now I said that whenever you have two kets like this implicitly means you're taking the tensor product. So it might seem like I've confused things even more writing it out this way because we have all these extra tensor products we have to calculate, but we'll see now that that's quite easy to do, and it shows why we work in the computational basis. So remember, what is, well, 1 in the computational basis is just 0, 1, because we're going to look at this tensor product specifically for now, and 0 is 1, 0. So if we take the tensor product of these two, what are we going to get? Well, we know it's going to have 4 elements, 1, 2, 3, 4. And this first element is going to be 0 times 1, which is 0. The second element is 0 times 0, which is 0. The third element is 1. And then the fourth is 0. So anytime you're tensor producting things in the computational basis like this, you just get one element in a larger vector. And if you count down how far this 1 appears, this also happens to be the value of this combined bit string, 1, 0. So we have 0, 1, 2, 3. We have 4 possible values for 2 bits, which makes sense. So just tensor producting 1 and 0 gives you this value, 1, 0. Okay, so now that we've talked about tensor products, how are we going to construct a quantum oracle that's going to be reversible? And now we can use our knowledge of multiple qubit systems to be a little smarter about how we want to compute f of x. So not only can we prepare an input register, let's say with n qubits, and when I say n qubits, that means, for example, if we have 0 we have 0 for n qubits, that's just 0 tensor n times. And the dimensionality of this entire state vector is going to be 2 to the n, so it's going to have 2 to the n elements. And that actually is kind of important that it grows like this. It's one of the strengths of quantum computing is that with just a small number of qubits, you obtain a state that is exponential in its dimensionality. And if you're clever, you can exploit that high dimensionality to compute things faster. And in the following videos, we'll see how we can try and do that. But in general, it's not as easy as that. However, this is a good thing to make a note of, that your state space grows exponentially with the number of qubits. Okay, so that's what I mean when I put this subscript n here, that it takes n qubits for this bit string. And this is our input. And not only that, but we can tensor with the output register. So we can prepare an output register, we'll call it y, and let's say it has m qubits. So in total we need n plus m qubits, depending on the problem. And let me move this over here. Okay, so here's a way that we can make it reversible. We keep x, we keep the input, but then we change the output to y, and then we XOR y with the function value. And this is indeed reversible, because let's say we wanted to apply this one more time. Well, then this is going to give us x again, and then y XOR f of x XOR f of x. And anytime you take the XOR of two of the same bit strings, you get back 0. And then anything XORed with 0 is just that thing. So this equals what we started with, and it is certainly reversible. Okay, so for example, what happens if we prepare y in the all 0 state? So y is just a bunch of zeros. Well, like I said up here, if you take the XOR with 0 and some number, you get back that number. And if that number is our function value, then we have a circuit here that computes, well, we have 0 here. So we have a circuit now that puts f of x in the output register and keeps the input register the same for us. And it is reversible, as we showed up here. So now we've introduced this quantum oracle model of computation, and in the following videos we're going to see firsthand how we can actually use it to obtain as much information as possible about this f of x with only access to this unitary, this oracle.